when all the body plans of the animals were evolved, went 100 times faster. And then those body plans were used by evolution to concentrate on higher cognitive functions. And biological evolution kept accelerating in this manner. Homo sapiens, our species, evolved in only a few 100,000 years, relative blink of an eye in biological evolutionary terms. And then again, working through indirection, biological evolution used one of its creations, the first technology creating species, a species that combined a higher cognitive function with an opposable appendage, our thumb, so that we could manipulate the environment and change the environment to reflect our models of what could be. That only took a few tens of thousands of years. Fire, stone tools, the wheels, these first steps in technology were a little bit faster than the evolutionary process that gave rise to our species. And then we used the latest generation of technology to create the next stage. So technological evolution also accelerated. Half a millennium ago, the printing press took a century to be adopted. Half a century ago, the first computers were designed pen on paper. Now computers are designed in only a few weeks' time by computer designers sitting at computers using advanced computer-assisted design software. And what's interesting is you see that this is a straight line reflecting an ongoing acceleration on this logarithmic graph. And it's also interesting to note that technological evolution is right on that straight line with biological evolution. It's a continuation of this evolutionary process. What is it that's evolving? Well, it's increasing levels of complexity and basically of intelligence as reflected in these evolutionary processes. Now, some people said, well, okay, Kurzweil just put points on this graph that fit on the straight line. So what I did is I took 14 different lists. And these were not people or research works that were trying to make my point. These were just what those reference works or thinkers, such as Carl Sagan's Cosmic Calendar, the American Museum of Natural History, the Encyclopedia Britannica. It's what they thought were the key events in biological evolution and or technological evolution. And you see some spreading of the points because there is disagreement as to what the key events were. People disagree how long the Cambrian explosion took, when agriculture started, and so on. But you see a very clear straight line. There's an inexorable acceleration that is inherent in an evolutionary process. And we see this if we actually simulate an evolutionary process inside the computer. Now, information technologies actually accelerate even more quickly. Paradigm shift rate is doubling every decade, but the power is measured in price, performance, bandwidth, capacity, throughput of information technologies is doubling every year. And you can go buy a digital camera today, and if you look at what you'd pay for the same specs a year ago, it was twice as expensive. And generally, we put that extra money not just into buying the same thing for less money, but to actually get a more capable product, a more capable technology, combine for maybe a little bit less money. When I was at that school down the street, a computer that took about the size of this room cost millions of dollars, is less powerful than the computer on your cell phone today. But this is just one example of many. It's really a very pervasive phenomena, and I'll quickly show you several examples. Computers, I put 49 famous computers on this logarithmic graph, going back to the first data processing equipment that was used in the 1890 census. Used these old punch card machines. I think they were subsequently shipped to the Florida Election Commission. In the 1940s, Alan Turing cracked the German Enigma code using a computer built from relays. In 1952, CBS predicted the election of a U.S. president, President Eisenhower, in 1952. First time the networks had done that using vacuum tube-based computers. They were then shrinking the size of vacuum tubes, making them smaller and smaller to keep this exponential growth of the price performance of computing going. That paradigm hit a wall. Every paradigm does finally hit a wall, and that it couldn't shrink the vacuum tubes and keep the vacuum. It was the end of that paradigm, but it was not the end of the overall exponential growth of computing. When one paradigm comes to an end, another one picks up the pace. So transistors came, application in radio. Transistors are not small tubes. It's a different technology. It kept the exponential pace going. So Moore's law, the shrinking of transistors on a chip, on an integrated circuit, was not the first, but the fifth paradigm to bring exponential growth to computing. And the end of that paradigm has been predicted for many years. The first predictions were that Moore's law would run out of steam in 2002. Today, Intel says 2022. But I would say by the teen years of this century, the key features of transistors will be a few atoms in width, and we won't be able to shrink them anymore. That'll be the end of that paradigm. But we'll then go to the next paradigm, the sixth one, which is computing in 3 dimensions. Chips today are very dense, but they're flat. They're 2-dimensional. Our brain, for example, is organized in 3 dimensions. We live in a 3-dimensional world. We might as well use the 3rd dimension. And that will continue this exponential growth well into this century. We see the same thing in supercomputers. I'm not going to dwell on each of these charts. You could buy 1 transistor for $1 in 1968. You could buy 10 million in 2002. And unlike Gertrude Stein's roses, it's not the case that a transistor is a transistor. As we've made them cheaper, we've also made them better. They're smaller, the electrons have less distance to travel, so they're faster. We've had exponential growth in the speed of these transistors. So the cost of a transistor cycle, you combine these 2 phenomena, has come down by half every 1.1 year. And then you add some other types of innovation, you get an effective doubling of electronics and computers in terms of price performance every year. And that's basically 50% deflation. It's a deflationary process in information technology. And depending on what week it is, the economists will worry about deflation. We had deflation during the Depression. But that was a completely different phenomenon. That was a collapse of consumer confidence, a collapse of the money supply. This deflation is really caused by an improvement in price performance. But the economists will say, well, okay, that's fine, but if you can actually buy the same stuff a year later for half the price, people might buy a bit more, but they're not going to actually buy twice as much. So you'll have a gradual decline in the size of the economy, at least as measured in dollars. But that's actually not what we've seen. We've actually seen the doubling of the consumption of information technology at more than doubling each year, more than keeping pace with this 50% deflation. We've had 28% annual growth compounded for the last 50 years in dollars in information technology. People didn't buy iPods for $10,000 10 years ago. Every time allows some new application like an iPod and all of the myriad of new systems and devices that we see, new applications are born, and the consumption of these grows at even faster paces. Magnetic data storage, that's just another example of the same phenomena. I only put this up here just to make the point that it's not just Moore's law. These are different engineers, different companies, the same exponential process. And what's interesting, if you look at these graphs, these very smooth exponential progressions, it looks like the output of some tabletop experiment. But keep in mind that these graphs are measuring a worldwide chaotic system with millions of participants and hundreds of millions of customers and IPOs and bankruptcies and competing companies and countries accusing each other of dumping products. And out of all of that unpredictable, chaotic human behavior come these smooth exponential progressions. You might wonder, how could that be? Well, we see the same thing in many other areas of science. I mean, take the path of a single molecule of air in a gas. A single molecule will follow a very chaotic path. You can't predict it. And we can't predict the path of any of the molecules. Yet the overall gas, when we measure its properties, has very predictable properties according to the laws of thermodynamics. So if you have a complex system, like the competitive system of technological competition, the overall properties of that turn out to be very predictable. And that can enable us to build scenarios of the future. Now, one of the profound implications of that is, as I mentioned earlier, we're understanding our biology as information processes. We have about 23,000 little software programs inside us called genes. These evolved in a different era. One of those little software programs, called the fat insulin receptor gene, says basically, hold on to every calorie because the next hunting season may not work out so well. And that was a good program when it evolved, because calories were in fact few and far between, and it was in the interest of our species to hold on to every one. We'd like to change that program now. We actually have a new technology that's just emerged in the last couple of years called called RNA interference, which we put little fragments of RNA inside the cell, and it actually can inhibit selected genes. It actually can turn genes off.